Hello and welcome to the episode of...
Don't even try.
I always try to do the numbers. Anymore. I don't know why. I never know what number it is. Welcome to the CADimensions 3D Printing Podcast. We want to be able to empower engineers everywhere with the best tools possible so that they can then go impact the world and stuff. And we think this podcast is just a small way that we can do that. We have to acknowledge that our set is a little bit messed up right now.
A little bit. Because
we had an awesome delivery earlier today. We are actually getting rid of the Connex 500 and we are replacing it with a Stratasys J750. And so there's a large crate there, but that's not actually the 3D printer. That's just the material cabinet. Our actual printer is behind that door.
Do you want me to do it?
Cue the door.
Cue the door!
You didn't even introduce me yet.
Oh, that's fine. People should know who you are by now. We've done at least 7 of these.
And behind, door number 1.
It's really, you get a really good understanding for what it looks like bound in a metal, in a wooden crate there.
Yeah, the crate is massive.
Yeah.
It's
it's
we
not,
have,
you
we
know,
have a bend for scale.
But it does look really big right there. But I remember going to, seeing these, in a row at the Stratasys corporate headquarters. And kind of interesting to see, like 10 or 15 of them lined up in a really large production facility. So
definitely.
Did you see a group of 900s?
I did, yeah. Those are large machines.
Yes.
But
Kevin,
they do some pretty neat stuff.
I think that crate might be bigger than your car.
I have a Mini Cooper, so it's really likely.
It's not that hard. It's not that hard to have a bigger crate.
No, it's a really low bar.
I don't mean that in a mean way. Naturally, I drove an Elantra forever. But anyway, we should introduce ourselves. So Ben is behind the camera.
Hey guys.
And then we have Ken.
Hello.
And then we have Kevin.
Hey.
And I'm Adam. We have a handful of exciting stories to talk about today. Essentially, we're in the time of year when companies are announcing all of their new products, which is a fun thing to talk about.
Holiday shopping season, right?
Yeah, holiday shopping season.
Trade show time.
Trade show time.
Yeah, that's true.
Put together your list for Santa.
Yep.
Or for your president so that they can buy you more equipment next year.
Next year's
more
budget.
Accurate.
Right.
But, anyway, the very first one that I wanted to talk about was a pretty cool story because it's about carbon fiber 3D printing, and that's always a fun topic.
Yeah.
And this company was revealing, I guess, their new product line at TCT Birmingham, and they are doing continuous carbon fiber, which is what Markforged is usually known for. But they're doing it a little bit differently. So what they do is they're doing it with what they call co-extrusion. And so what Markforged does is they put down plastic and then they put down some carbon fiber, repeat that over and over again.
Different nozzles.
Yes, different nozzles. They put the carbon fiber and the plastic in the same nozzle. And so it all comes out the same area.
Kind of like a pencil. Like it's got graphite running through it, and it would like you lay it out in one.
Sort of.
That's the best analogy I could come up with.
Imagine like the letter Y. So you've got fiber in here and plastic in here, and the plastic melts and like coats around. I just bumped the microphone.
Yeah. Okay.
Coats around the fiber real nice, and then it lays it in the print.
So then the layer that comes out, the what do you call the layer line? I guess the bead is like a hard plastic surrounding the carbon fiber.
Yeah,
correct.
Okay. Yeah. If you think of it
like a pencil, with wood surrounding graphite.
You're
that was
still,
the analogy I was going for.
I was not following that at all.
When you said pencil, my mind immediately imagined mechanical pencil, and it kind of scares me now that that's exactly what I thought about. Wooden pencil didn't even come into my brain when I imagined a pencil.
I'm older than you.
What is this world we live in? But anyway, Tom Sandlager or whatever, one of the
Sandlander. I don't know. There's too many vowels.
Tom S, 3D Printing Tom on YouTube, did a video interviewing them at TCT, and their parts looked really, really cool, and they had awesome strength properties. So I wanted to kind of ask the question, what is better, or opinions on continuous carbon fiber, like we're seeing from this is Anisoprint. I think they're a Russian startup. So
that's what it looks
like. They just launched in the UK, so they're not even over here yet.
Right. like them or Markforged, or chopped carbon fiber like we see also with Markforged, but with a lot of other 3D printer manufacturers.
Yep.
Ken, what's your take on it?
Opinions? Okay. So the continuous carbon fiber is really, really good if you want strength in one direction.
Mm-hmm.
So specifically with how, I kind of picture how, what is the name?
Anisoplate.
Anisoplate?
Anisoprint.
Anisoprint, got it. Anisoprint, and how Markforged does it is, if you bend the material in one axis, it will be extremely strong. But if you bend it in the reverse axis or go against the layers, it's going to be just as weak as any other FDM print.
Even with carbon fiber?
The splitting of layers will still be the same weakness.
Right. The layer-to-layer strength is typically the weak point in 3D prints.
Mm-hmm.
Mm-hmm. So
where those two layers fuse and meet together,
yes.
Right.
That's where there's vulnerability.
And that's not a problem that's being fixed.
So that doesn't
with the
address
continuous
that.
fiber.
So
this doesn't address that. Okay.
Really what the continuous fiber is addressing is just raising the maximum strength level in one direction. One or two, depending on how you print it.
Does that really
on
only...
the X and Y.
So
X and
I'm
Y,
looking
yep.
at the picture. You can't see this, I realize. The picture, and it's a cross-hatching, and it looks like it's, infill for something that like somebody might stand on.
We'll put the picture on the screen. Looking at
Hey, thanks for making my
Ben
job easier.
Ben will overlay it for you guys.
Yeah.
We haven't done enough of that.
So the debate with Markforged and now with these guys as well will be the lack of the Z capability.
Yeah.
So they lay down carbon fiber in X and Y. What's holding back those parts from really taking the next major jump is being able to print carbon fiber in the Z direction upward.
Okay.
Which one company in the United States, it's a startup, is kind of doing.
Are they using a multi-axis printer?
They are not.
Okay.
They are using...
Because that is one way I've seen them get around it, is actually just to move. So if you're always printing down, you're now with a multi-axis printer moving your nozzle to a different direction.
We taled about that in the last podcast with non-planar 3D
You're
print. Wow,
so excited
all
about
these
that.
stories.
Not non-planar.
Axis.
Axis.
Oh, on an axis.
Yep.
Okay.
More like the
that's a little
7-axis machine.
Okay, fair enough. There's a startup in the United States near Boston where they are printing with a DLP printer, and then they can use long carbon fibers and manipulate them with electromagnets so that they can position them in theory however they want. Now I don't think it's a real product yet, so we don't know
It's
how
gonna be
it'll
tough to manipulate
perform.
too. I mean,
I'm sure
kind
it's
of
difficult.
Utilize a magnet to control something that precise is going to be a challenge,
Yeah.
right, to say the least. So that's
Yeah,
kind of tough.
and there aren't a lot of details on how that one works yet.
Yeah.
So I guess we'll have to
Sounds cool.
keep in mind.
It
here.
does. Kind of like the Vulcan metal 3D printer, right? Doesn't that do something like that?
Nope.
Nope.
Not that I know of.
Okay.
No.
Never mind.
different process.
Find me an article, but I'm not really sure where you're going with that. But anyway, chopped carbon fiber versus continuous. Personally, I'm not really sold on continuous carbon fiber. I think it's really cool, and I love seeing like the different iterations and improvements that it's gone through in the past few years.
There's got to be some good applications for it, right?
Maybe, but it could make more sense just to put more chopped carbon in your filament mixture.
Mm-hmm.
Or even there are some companies that do pellet extruders where you can put a whole bunch of glass reinforcement or
Glass-filled, yep.
carbon fiber reinforcement in with your plastic mixture.
Mm-hmm.
All the carbon fiber really does is make it stiffer. And so it kind of seems, I don't know, over-engineered or a little overcomplicated to be placing these specific strands in specific places, whereas going back to the uniformity of strength, generally speaking, that's how parts are the most predictable. And you get more uniform strength by doing a chopped mixed plastic compared to having specific strength reinforced areas.
So then chopped is exactly what I'm thinking about. So we're talking about almost like a spool of or thread of carbon fiber woven into the material, so it mimics the layers and does all of those things. But you're talking about
that's continuous.
That's the continuous.
Yeah.
But then in contrast to that is your filament is a mixture of chopped bits of carbon fiber with plastic, so it's more integrated.
Exactly.
And I get that. That does make more sense.
It's a lot like our desktop metal machine where the feedstock is a combination of plastic and metal.
Right.
This is a combination of plastic and a stiffening agent, usually glass fiber or carbon fiber, and so we can just print with that.
Right.
And I think that does a better job of making a part that predictably performs. And it's not as complicated to print with. Like, you don't have to program special toolpaths on where the continuous fibers go or anything like that. And if you need strength in a specific feature, you can always add like a metal insert after the fact. And that's probably an easier way to go than buying a special machine to inlay fibers.
I could buy that.
Yeah, my only question would be, because I know a big topic right now is simulation of additive parts. Obviously, that's a very big deal in metal for like aerospace, but even in plastics. So you can't go into SolidWorks and make a part out of solid ABS and say, "Oh, this is how my 3D printed part's gonna react."
Right.
It's not true.
Because it's not uniformly strong.
Yes. So
in every area, because
I
of the
just
layer thing
wonder.
we're talking about.
I just wonder if more isotropic parts will be easier to simulate.
Right. That's my point.
Because otherwise, with simulation software, you're going to have to start being able to specifically lay out basically strips of different material of different stiffness to.
Right.
You have to customize that. So it's just adding a layer of
complexity
to the simulation process. Because I think that's the next bar for people who really want this high strength plastic for really critical applications.
Right.
They need to be able to predict it.
Exactly. I think to your point, as the demand for high strength 3D printing increases, that's going to bring along with it an increase in material price. And when the material price comes up, people are going to want to simulate it before they print it and test it, because all of a sudden, exactly, they don't want to just be wasting money if it doesn't work. And the simulation gets more complicated. Again, not a simulation expert, but it stands to reason that it would be more complicated
the more variables you bring in.
If you've got strands, and then you start worrying about the accuracy of where the strands are located.
Versus, again, if you're saying, like, I'm building this part out of steel, the whole thing is steel. If I'm building this part out of aluminum, it's all aluminum. If I'm building it out of carbon fiber impregnated material, it has that characteristic throughout. You don't have to make special
hopefully
allowances.
With like our carbon fiber nylon, you'd be able to say, understanding it's an additive process, it is nylon 12 with 35% carbon fiber.
Yeah.
And the computer would be able to treat the entire part as that.
Right.
Obviously, it's still going to need to factor in
the layer strength.
Layer strength, essentially.
Right.
Which is why I'm a little bit more partial to the chopped carbon fiber, because you're just printing with a homogeneous mixture, just like you're printing with a single plastic. I think there's probably specific applications where you need one or the other, but as a whole, I just think it adds more complexity than you really need. But actually, our next story, Ken found it, and it was super cool. And this is something that actually addresses the layer-to-layer strength issue. Did you want to dive in more and talk about it?
Do you have what it's called up? Because I can't pronounce the word.
Oh. So it was a research study.
Oak Ridge National Laboratory. Yep, down in Tennessee.
Okay, I should have remembered that. That's a pretty well-known laboratory. And they were using UV irradiation.
Irradiation.
Irradiated.
Irradiation.
Irradiation?
Irradiation.
Or is it irradiation? It's very confusing. Anyway,
this is why I'm not getting into this discussion.
It's
I think you're right.
I think
irradiation.
Irradiation might not even be a real word.
So, like, I'm teaching my son to read. If I cover off the first IR, I have radiation. I think
it's a typo. I don't think that's a real word.
I'm looking at how to phonetically say it. Irradiation.
Yeah, okay, we'll just go with that.
I win. I think I won. I think I pronounced it right.
Anyway, why does it matter?
They use UV radiation.
Sure, we'll go with that.
Okay. And what are they doing with it?
So essentially what this is doing, and I don't know, I'm not an expert on that technology, but they're doing this to increase shear strength by over 200%.
Okay.
Yeah, so that's a lot.
I don't think I saw that number, but that's pretty impressive.
That's a lot. So I'm assuming shear stress would come on the layer-to-layer side.
Okay.
It's more of like a
they did
shear.
say that was the problem.
I've got this open right now, and it's saying that, basically there are many methods of 3D printing, FDM being the most popular, but layer adhesion, like we were talking about before, is a problem among all of them.
Yep.
So it can, make them unnecessarily brittle. They can't handle as much strain. So yeah, they are basically, like you said, trying to change the molecular chemical bond that exists between those layers by hitting it with a special UV
Radiation.
nuclear
UV
radiated something.
Hey, a non-engineering guy has a question over here.
What's up?
Can you explain to me the difference between that and sintering?
So sintering is high heat for metal.
And what does it do on a molecular level?
It's more of a partial melting.
Yeah, so it heats the metal to just below its melting point so that metal powder can fuse together.
So the quote from one of the people at this company here, what is the name of the company?
Oak Ridge National Laboratory.
It's not a business, it's a research place.
So the name of, representative, Mark Dadman, he was saying that,
Mark.
His quote is that the chemical bonds across the layers of printed product will strengthen it because now the molecules are bonded together as opposed to just the layers being bonded together and the molecules floating freely.
Right.
So it's just, I guess my question would be for you guys, do you see a difference between this and, what was the process we called it where you bake it?
Annealing.
Annealing, that's the word I couldn't think of.
You are like
Is
reading
this
my
chemical
mind.
annealing almost?
You're
or
reading
UV
my mind
annealing?
because honestly, I'm not to disparage Oak Ridge National Laboratory. I don't see what the big deal is. Annealing of plastics has been around for a long time, and it hasn't really been applied to 3D printing, but annealing has been around for a long time.
Mm-hmm.
UV ovens have been around for a long time and are used today for sterilization and all sorts of different stuff. This seems like kind of the same thing to me.
Well-worn territory, maybe.
What?
Well-worn territory, maybe.
Exactly. And
Well, even with knife making, like every time I've made a knife, I've had to heat treat it. It
Mhm.
sounds like it's the same thing.
But I mean, for plastics, it seems like they're just using a different heating.
Process, same
They're using a different heating method to accomplish the
But-
annealing.
But it's a chemical reaction.
I don't know.
It's not necessarily heat, it's chemical.
Yeah, so with the heat, I guess the difference I'm thinking of, and again, not knowing all the details, when I think of annealing, I think again of almost like a borderline melting.
Yeah, that's what I was going to say. Like it's
But
melting
it's a
plastic
thermal-
together.
But radiation
It's a thermal
causes
change.
You're
heat.
saying irradiation. You're saying radiation.
I think it's the same thing.
Is it, well...
Maybe this is why we're not research scientists.
Wait, in the YouTube comment section, it's irradiation and radiation.
So Google beat me to it because the only irradiating I can think of is like beef. You irradiate beef, like you poke holes in it, right?
Do you?
I don't think that's the same thing.
No, no. So that's all Google's giving me back. So Wikipedia is going to be no. Okay, no. The process by which an object is exposed to radiation.
So it's the same
Wow, I
thing.
stand corrected. Adam. I'm so sorry, man.
So by extension, you have a lot of different types of radiation. Why not just throw some 3D printed parts in the microwave and see if they get stronger?
So I haven't tried the microwave, but I've tried an oven.
Okay.
I've tried annealing
Are
PLA
they stronger?
plastic. Yes, but the predictability and warping was a huge problem.
Okay.
So probably because I was using like a toaster oven in college, and it wasn't very good. So the problem with our oven that we were using is to do this kind of process, you need a very controlled temperature.
Mm-hmm.
Where most like at home ovens will use a kind of like I'm forgetting what the system is called, but if it'll heat it up, and then as the temperature slightly drops, when it hits a point, it'll turn the heater back on. So essentially the heater is on or off.
Mm-hmm.
There is no like stable. It's either
Okay.
heating or it's cooling.
Right.
And it's just keeping it in a threshold. You need an oven that is very controlled, where either that threshold is 1 degree or you're constantly holding at a controlled temperature.
Sure. But those types of industrial ovens exist.
Mm-hmm.
Industrial. So maybe this could be an opportunity for
Again,
smaller
you know,
scale.
I think this is also different from heat because as I'm reading Wikipedia, which is of course the source of truth in the universe,
Naturally.
it's giving analogies rather to like sterilization, like using radiant light to sterilize something. So I would think of like if I have a jar of test tubes or a pile of test tubes that are going to be sterilized using UV light. That's not heating them up.
It is.
Technically, yes.
The light causes heat. So you get radiation from the sun.
Yeah.
Some of it's light, just like UV light.
Right.
And it hits stuff, and it gets warmer.
See, that's why I'm in marketing and not a scientist.
So
Know that it's called sun.
Not that I didn't need to know that the sun is hot.
the sun is hot, Kevin.
I'm learning something new every day.
Ken, going back to your point with the toaster oven, I have wanted to do this experiment here where we just fill our part with sand and then put it in the oven, and then the sand would help kind of keep the heat or the temperature at a more stable.
Some people have done that, but
Yeah.
instead of filling it with sand, you just put it in a sand bath to try to keep the dimensions
Just
where
put
they
it in
are.
a sandbox.
In a whole box of sand during the annealing process.
I didn't explain myself well, so thank you for knowing what I meant. I could see.
I picked this story because I know how crazy you are about annealing, and I thought that this would just be a great conversation. But anyway, the article isn't super detailed. I'm not sure we can come to any actual conclusions here, but it's kind of neat.
It's a really cool headline.
Yeah, really cool headline, and I think that the layer-to-layer issue needs to be solved, or will be solved eventually in some way, hopefully.
But it seems like people are applying a lot of different methodologies to try to fix it. So they're getting beyond annealing. They're trying different tools, different things. So who knows? If it's not this, hopefully there's something else.
I can only imagine that there's pluses and minuses to each method.
Sure.
I guess
Naturally.
so. So we talked about continuous fiber. We talked about fixing the layer issue, and all of these kind of revolve around people wanting stronger parts.
Mm-hmm.
And so, again, at TCT Birmingham, Zortrax, they're...
Zortrax.
What?
I'm dating myself. It's an old movie reference.
Do you understand it, Ken?
Don't worry about it.
Okay.
The internet will get it.
He's like 15 years older than us, so.
The internet will get it.
Internet, please make Kevin feel better.
Zoltan.
Zortrax, prosumer 3D printer manufacturer, released a 3D printer that they're aiming at printing PEEK. PEEK is a very high temperature, high chemical resistance, high strength polymer, and I wanted to talk about it because this is kind of a trend that I've started to see lots of manufacturers come out with high temperature machines.
Yep.
Are you seeing the same thing? You seem to be agreeing with me.
Yeah, I've seen probably, I can think of at least 4 companies that have released a small format high temperature machine.
Yeah, and like 3 years ago, none of that existed.
Yeah.
There was
none of
there
that
was
existed.
Stratasys, Ultem, and even our PEEK is relatively new, but not.
Yeah.
It's been like a little over a year, but
Yeah.
We've had high temp capability, but not PEEK. You've
Right.
really started to see the PEEK push this
We've
last
gotten to
couple
the peak of
push.
peak.
peak. We're in the peak of the peak. Yeah, we've seen a lot of small format machines pop up.
Right.
So this company is doing something different with this now, or it's a prosumer.
It's a new product
model?
for them. So they've done printers that'll do the normal PLA ABS for a while now, and now they're kind of stepping their game up to high temperature plastics. Like Ken said, Stratasys has been doing this forever,
Right.
or at least for the last decade or so.
The high temp stuff, yeah.
Yeah, the high temperature
Not necessarily
printers.
just PEEK.
So I think it's pretty cool how some of these smaller companies are finally starting to catch up. A lot of that has to do with some of the Stratasys patents expiring. So Stratasys invented FDM, and they've profited off of it, as they should, for inventing the technology for years, but now those patents are expiring and other players are coming at the game.
But the material patents. Those are not the same.
Not patents on materials, patents on things they put on the machine that allows it to print that.
Yeah.
So the big
Like
problem,
insulation, motion systems.
yeah,
those
the
things.
big problem with high temperature systems is really, it's not that the fact that we can't make an oven. We're really good at making ovens. We got that down. We also are really good at making high temperature nozzles. That's not an issue. The issue is, like, if you're using a belt driven system, will your belts melt when you get up to that temperature?
Right.
Will your control boards fry? Like, putting in the proper...
What kind of temperatures are we
installations.
talking about?
Hotter than your oven now.
So I'd say probably you're
As
looking
hot
at...
as, or hotter.
400C, like.
Yeah.
Can we use
get
freedom
there.
units? Can
we
we send
what?
freedom units here? I don't know. What is 400C?
Oh my god.
God.
Freedom units. You totally threw me off here. 300 Celsius. The international system of measures. Ben. Not American imperial units.
Going back to the patent thing, so Stratasys has a patent for that system, and the reason you've seen a delay is other companies have had to come up with new ways to do it.
Yeah.
Right.
Right.
Exactly. So they've been designing around the patent so that they can print with these high temperature materials. But I guess I wanted to throw a bit of a prediction out there. We've seen so much hype around metal 3D printing, and from a lot of customer conversations, I've found that they're familiar with cheap 3D printers and low temperature materials, and then that forms their whole vision of what 3D printing is, and so they think they have to go to metal printing. But in reality, there's this whole world of high strength plastics, and it can be done more often than not faster and cheaper than printing in metal. And so my prediction is that over the next 2 years, we're going to see a lot more high strength plastic companies and applications come out. As people
versus metal.
Yes.
Okay.
I think metal's going to be further away than 2 years. I think it's going to be easier for companies to create a high temperature plastic machine than it is to create a metal system. I think metals are probably going to take another 4 or 5 years.
Because now you're not necessarily, well, I guess my thought on that was, consideration of materials, right? Unless the materials are relatively standardized for that. Something like if you're making a metal machine, you've got to work with a specific metallurgy to get a material that works for you.
It's more complicated.
Yeah.
And Stratasys, again, has been doing high temperature, high strength plastics for a decade. And so there's a lot of knowledge around that already, and it's really just an extension of the cheap 3D printers.
What's the temperature difference between like a desktop metal printer and a printer that's printing in peak?
The desktop metal process?
No. Like the internal, as you're baking your part in a desktop metal printer versus your printing.
It's hard to draw a comparison there.
Yeah.
So
different technologies.
Yeah, they're so different.
Yeah.
Like I put my GoPro inside the printer while we were printing in desktop metal.
But if you did that when we were printing Ultem on the Fortis, you wouldn't want to. It would be too hot.
Right.
And so printing, it's different.
Okay. Different works. I was just curious.
It's different.
You're not. The thing with the desktop metal is you're not melting metal. You're melting
Plastic.
thermoplastic,
Right.
which contains metal powder.
Which is pretty low melting.
So you don't actually have to hit high temperatures.
Okay.
Until you get to the sintering step.
Yes, that's when you get into the 1200 plus degrees Celsius,
Which is hotter.
which is hot.
Right.
With our machines, you're talking like 300 to 400 Celsius range in nozzle temperature just to extrude the plastic, and then your chamber temperature, your environment needs to be somewhere between 100 150. Depends on what you're doing.
Hey Ken, did you ever burn your hands on a printer?
That's a big yes.
That's a yes.
I got a story for you after this.
I tried grabbing an Ultem part this morning that Ken took off the printer, and he was like, "Oh, here." And I went to grab it.
No,
Okay,
don't put this on me.
He was holding it, and he was wearing gloves, and I was like, "Oh, it's probably not that hot," so I reached out for it, and he didn't let me. He kept me safe, thank you, Ken. But we've talked so much
He learned from
about
his mistakes.
we've talked so much about high strength parts, and that's not the only area where 3D printing companies are making announcements and making advancements. So we wanted to switch gears here, and the next thing I wanted to talk about was more of an aesthetic. And so we are getting a J750.
Yeah.
But by the time this airs, Stratasys will have announced the J850.
Mm-hmm.
And what that does is it adds another.
Adds one.
It adds one.
Actually, it's 100.
Or 100.
Or 100.
What it does is it adds one material to the printer. And
Okay.
so
for those who don't know, J750 is a polyjet machine.
Yes.
And it's different than the fused FDM technology that we talked about the rest of the podcast.
Yep, exactly. So, real quick explanation. Polyjet works a lot like an inkjet 3D. Works a lot like
Printer.
an inkjet printer,
Yes.
but instead of putting ink onto paper, it puts photopolymer resin onto the build tray. It ejects that as a liquid, hits it with UV light, and it turns into either a solid or into a rubbery-like substance. Because we're printing with a liquid, we get two big advantages. One, we can blend them together while we're printing, and so you can do multi-materials in different colors. that blends into this conversation, and you can print in super fine layers, so you get a really nice, smooth surface.
And I believe the J750 is the only printer in the market that has Pantone certification for its color optimization, so
that's correct.
If you're trying to print something and it's your specific brand Pantone color, you can guarantee that it's coming out like that.
That it
nice.
is that color.
Yeah.
So with the J750, it has 6 model materials and 1 support material. The J850 has 7 model materials and 1 support material. I almost completely blanked there. Thank you for saving me. And the thing I wanted to talk about is, why is that even important? So starting out, Kevin, if you were going to make a color in Photoshop or whatever, how many colors would you need to combine to make that color?
It depends.
Okay. Well, what are the base colors?
What colors do your printers at home have?
I mean, your primary colors are blue,
Yeah.
What
red, green,
Magenta.
Okay.
Black,
More.
white.
I'm liking this magenta
black,
thing.
white.
So what are they? We've got CMYK.
Cyan, magenta, yellow.
That's almost
black.
like it's a setting in graphic design while printing in either online or in print.
Or RGBs, red,
Right,
green,
right, right.
blue.
And so when you're printing on paper, it's relatively simple because
Right.
you have those, and then you print on white. You're pretty much always printing on white.
Right.
But so that's only 4. So the
CMY, K.
CMY, black, and then so now we need white
Yeah.
because we're printing in 3D, so we need something to print on. So that's 5 materials. But we might also want flexible materials, so then we need to add a flex.
Or clear.
And we might also want clear materials, so we have to add 7 materials to be able to really do everything that a product designer might want to do.
Flex isn't a color.
Flex isn't a color.
Everything else you listed is a
Everything-
color.
Well, is clear really a color?
Transparent. So okay, so
Is transparent
magenta is its own material.
Yes.
Okay.
So you have CMYK, white, because normally paper is white. So
Right.
we're replacing paper with white material. And then clear, because you can't make clear unless you have clear from the start.
Right.
And then the flexible being think of more of we're using a flexible white material
Yep.
that can blend with any other color to basically, I don't want to say bleach itself, but blend
It'll-
it with the color to become more
It'll
like
adopt the
color.
color that
Yep.
you're. Yeah, I get it.
So not only will parts
For the purpose of being.
more realistic.
Yeah, I get you. Okay.
So before we had almost all the way to a realistic part, it would be colors would all be correct. Now we want prototypes to not only look correct but feel correct.
Right. Okay.
Yeah, that's actually a great explanation.
Very cool.
And so it's just another level of realism that people can get. We were so close before with the 750, but this is, unless we think of something else, this is pretty much the end of it.
Yeah.
Right?
Right.
And so you
Because
can...
it's down to you can control that
Yes.
to
Just-
the nth degree, right? Like
Yes.
the voxel,
Voxel,
level,
yep.
which is minutia.
Exactly. So
Like we could technically do our CADimensions color, which is
Yeah.
BB203B.
we could.
We'd have to translate that back to a Pantone color, but we could directly find it.
BB203B is a Pantone code.
Yes.
I don't know.
There you have it. See, this is the difference between marketing and engineering.
But this is
knowledge
where we meet,
is.
Adam.
This is where we meet on.
But
the
really,
3D
this is
printing
where marketing and
podcast.
engineering
Yeah.
meet, because this is where engineering comes and says, we're trying to, we need to get you a end result product, and the printer satisfies what marketing is looking for to create
Right.
these realistic prototypes
Because
to sell to
marketing-
investors or do whatever.
Gets really picky if the Pantone color isn't right. Most
Absolutely.
engineers are like, I don't care.
This doesn't follow our brand standards.
So
Absolutely.
both I think when from Stratus's viewpoint, I think their viewpoint is marketing's one, but sales and engineering being on the same page.
Mhm.
Sales,
Yeah.
engineering, and then in a typical prototype environment, you're talking about sales, engineering, and prototype manufacturing, which usually comes in the form of model makers, painters. What does a painter do when he needs a color? He goes, he finds the recipe, mixes up the paint, and then paints whatever you need.
Mm-hmm.
Essentially, we're doing that now we know the proper blends of colors to
We know
get
the recipe.
Pantone color.
Gotcha.
I had
And
a CEO once that I used to work for, and we printed, it was like 500 or 600 tote bags with our logo on it, and it was off by one shade of blue.
no.
And again, I didn't even see the bags yet. Like we ordered them, we have our codes that we use, and he holds it up in front of me. He's like, "Do you see what's wrong with this?" And that blue, without looking at our own blue, I'm just looking at it, like looking for a typo.
Like, it's a tote
This is
bag.
the wrong shade of blue. And he holds up a printed piece of paper. I'm like, "Oh, you're right. As a matter of fact, that is one shade off." We had to return every single tote bag.
Wow.
Thousands of dollars.
That's heartbreak.
That's a mistake that comes from what happens if that is a surgical model of something, and it's like that doesn't look realistic enough. Now you've got thousands of dollars,
Well,
or
what
you've
about
got a new
Coca-Cola
product.
Red? I mean, if it's
Yeah.
not Coca-Cola Red and Coca-Cola is printing it,
Right.
it may be close enough, but they're not going to accept it.
It's a
Right.
branding issue.
Branding is really important these days. And so being able to print real colors is very important
Absolutely.
when you're designing products so that you can, stand out amongst,
So this is a new machine.
amongst all the
So now do we
all
trade
the
in our
clutter.
new J750 and get a J800?
No, it's an upgrade.
850.
So
850, excuse me. Okay.
everyone who has a J750 today can upgrade it to one of two brand new machines that Stratasys will have announced by the time this is published.
Okay.
So the one is the J850, and the other one is the Stratasys Digital Anatomy printer, which Ken is very familiar with. He's been trained on it, so I'll let you talk more about it.
Here's our surgical
It's the
bear.
gummy bear. Okay. So yep. So the new digital anatomy printer. Obviously, as you can tell, this is designed more for
I won't break it, Ken.
Oh, jeez. The medical, either from the hospital perspective or the medical device perspective, and essentially what we're doing here. Okay. It's a mixture of software and materials. So from the material side, Stratasys has come out at this point with 3 new materials, one representing tissue, one representing bone, and one representing a gel. So obviously the gel is not a anatomy base, it's more of a way to make more realistic anatomy. So the gel would go more along the lines of like, how do we get support material out of a artery? It's much easier if it's a gel that you can push out or squeeze out than have to dissolve out.
Gotcha.
So the gel is the support material?
Sometimes, yes.
Sometimes.
Yep. So essentially, from the material side, they are having it independently tested that these materials actually act like human anatomy. So the goals of these models are not to look like your heart. They are for the doctor to be able to cut into, perform a surgery, test a medical device, train a new doctor on.
It'll respond like
They
flesh.
want it-
It'll
yes.
respond like the organ.
They want it to cut like it. They want it to bend like it, break like it, like with the bone, drill through it.
So like this, from what I understand, this is meant to be, as though these are stitch guides
Yep,
for
it's a suture
somebody to practice sutures on, and you have different examples here. But then it will respond as though your skin would when you're sewing
Pulling,
somebody
tearing,
up.
that's really what they're trying to simulate.
Yeah.
Um,
When you think about it,
Adam loves
when you
medical
think about it, when you're doing research, in your research facility or a hospital, like you said, or a medical device company, and cadavers aren't easy to come by. Models to work with that are really realistic, or very expensive.
Slight variation of what you said. It's not that they're hard to come by, it's hard to simulate specific things.
Sure.
So example being, if you created a new medical device for a very rare condition, or decently rare condition, it's very hard to find cadavers that have that specific condition. So the cool thing with printing this anatomy is I can get an MRI of someone who has this condition and perfectly replicate it.
Mm-hmm.
This is same for surgical planning. That's something that the rigid models have been used for a long time, is rigid models that literally you bring a team of doctors around to plan a surgery.
Mm-hmm.
So,
but it's mostly visual at that stage.
Yep, it's mostly visual. Mostly just like taking parts apart, and you could cut it and do some little basic things, but it wouldn't feel like the real thing.
Right.
But this you could do training for med students on. You could do training for doctors on. If you had a company that made medical device stuff, and when you have to go out and train the doctors in the field, you've got to rent space or do it at a hospital or do it something like that where you've got access to those materials to work with.
Yeah, so they kind of joked about it, but it's rather true. Is with this technology, you could pull a doctor into a cafeteria table and say, let's practice surgery here.
Right.
You don't need to have a cadaver lab. You don't have to have, the existing market with like silicone molds and some other things. They do a better job of replicating, but they're still not completely realistic. They don't respond the way the human anatomy would.
So we need to do an episode where I try to cut open and remove the heart from this little bear, since there's
You just really want to destroy the bear.
I don't want it. He's adorable. I like that they put "Don't eat me" because that was kind of my first
Legal
instinct. I love gummy bears, so that was a big hook for me. I think that would be fun. I think we should do that when we have the opportunity. I think it'd be cool.
So that's the first part of the anatomy printer, is the materials. The second part is the software, and that's really where the big revolution is. Doctors don't care to, I guess, when we print with materials, we say like, oh, to get this shade of red, we blend this much magenta, this much yellow, this much cyan, and that's how we get the color. Doctors really doesn't care about that. The doctor just wants to be able to say, I want to print bone. I want to print heart, liver, organ. Like they don't think in terms of materials, they think in terms of anatomy. So essentially the software, number one, it allows the doctor to pick. So they would maybe upload a femur bone, a model, and they go through a drop-down list of, they might say skeletal, and then they might choose femur bone. So not only does that give us the proper bone outer structure, but also the software does the internal part. So the bone marrow, the anatomy of the inside of a bone.
Wow.
So you don't have to model that all in before.
So you can print something as hard as a femur bone?
So it's not as hard. Your bones are actually slightly flexible. The issue with our older Vero models was they were rigid and they just snapped. Bones aren't like that.
Right.
So we're not only is this button printing the bone material, but it's also changing the internal structure to match that of real anatomy.
So okay, this scenario could be one where I am Dr. Kevin, MD, and I have a surgery tomorrow. So I come over to my J750 Digital Anatomy printer. 750 Digital Anatomy printer. I print, go on my right femur for a child age 12, something like that.
That you already have an MRI for.
I already have it. I've uploaded all of his information, and I can just hit go, come back the next day. All right, let me do this once first before this kid gets in here. I'll know exactly what to do. I can replicate this situation. That's one application. That's incredible.
They actually did that before. The surgeon down in Florida, that little girl with the messed up heart.
Holes in her heart.
Yeah, and he printed her heart with a CT scan. He printed it out like 7 times, practiced the surgery, and then by the time he was ready for her, he already knew her heart inside and out.
But again, she had a very specific condition, like you were talking about before. You don't find cadavers that have 5 holes in their heart of a little girl. Like,
exactly.
It's not something you're going to come across.
I don't know if you're insane. I guess
I am insane. Is that what you're saying?
No. I don't know if you're saying. This isn't something that's going to be done for every surgery.
Yeah.
Like, some things are so routine that they know how things happen.
Sure.
They don't need to print.
They're not
going
to practice to take out my tonsils?
Probably not.
How can I trust them?
Like you said, with very rare cases or something that maybe a doctor's new with or hasn't practiced before, this gives them the opportunity to practice a surgery. Now that's one side. That's the more of the hospital side, and also the training of new doctors. On the flip side, like we said with the med device, is you're creating that special anatomy to train doctors for new devices.
This can't be my desk, near my desk, because I'm just going to play with it all.
Please don't break that. Please don't break that. Please.
It's fun.
Thank you.
Or for testing, right?
Did you rip this one?
I didn't rip anything.
The tissue.
They're all getting little rips in them.
Yeah. If you bend it too far, just like your skin, it will rip.
So, and this is really, I mean, a lot of these are thicker, way thicker than your skin is.
How do you have children that are still alive, Kevin?
It's a miracle, Ben.
The teddy bear.
I have a very patient wife.
The teddy bear example, like, removing the heart from the teddy bear is fun, but that's not really realistic of cutting through skin.
Right, yeah, this is
to make that
skin.
most realistic, you would tell a doctor only go a millimeter or 2 deep and make an incision.
And then the rest of it would be flesh-resembling material, muscle material, and then you'd have an artery running through. You'd have your vena cava and the whatnots.
If you did a full model, yeah.
See, but this is more like a heart.
Yeah. Not in an anatomical.
Right.
Unless your gummy bears have hearts that I'm not aware of.
No, I'm not aware of
that.
Okay.
The other big area for this, if you're not at a hospital or if you're not at a med school, and usually those are pretty much in the same place, is for medical device companies.
Mm-hmm.
So pretty much every medical device company that I visited has a cooler full of chicken bones and pork bones and those sorts of things so that they can prototype something and then test it.
Mm-hmm.
If you're doing, what's the name for doctors who do bone stuff?
Orthopedics.
Yeah, if you're doing that and you're making bone screws and implants
Yeah.
and plates to stitch people back together, you have to be able to test that first.
Right.
And so it could be a great test opportunity, and then also, like Ken mentioned, to train doctors
Mm-hmm.
in how to use their devices. Med devices is such a competitive space, and you're usually pitching to the doctors, and then those doctors like vouch for you and want to bring your devices into the whole hospital.
Right.
So how you support and train those doctors can be so
or break.
important to actually like winning the business.
Yeah.
So it's proving and being first. That's the two themes we
Yeah.
constantly hear is, well, there's probably someone else thinking of making the same similar type device. I need to be first to market, and I need doctor buy-in.
Mm-hmm.
Right.
Without those two things, your product's not going to take off.
Mm-hmm.
And this is one way to do that, and it's more accurate than using pork bones because it's certified by the FDA and all these other people to be maybe not okay. Ken's shaking his finger at me. He went to
Not
training,
FDA.
I didn't, so ignore me. Listen to Ken.
Independent verification.
It's
not
more accurate than using pork bones, so you get better tests, and then the doctors get better training.
Right.
And when the doctors get better training, they want to buy your stuff, which is good for them.
Mm-hmm.
Anyway, I think we've
Going back to cadavers, that just seems like another reason why you don't need to buy a dead body.
There is an ethical
There's a lot
perspective.
of reasons why you don't need to buy
There's
it.
an
There's
ethical
one
part to
more
this.
reason why you don't need to.
I mean,
Hey, by the way, Ken, before we go to this podcast, if you could choose, what body part would you print?
I've had bad knees forever. I would print myself new knees.
That's a great response, Adam.
Thank you.
Thank you.
yes,
I don't
this is
know why
not
we
an
did a
implant
baseball.
technology. This is by no means an implant technology. This is a practicing technology.
Yeah, I had a surgery when I was in junior high that didn't go well on my knees. Had to go back and have a second one.
Both of them?
No.
That's why if you go into earlier podcasts, we were sitting while Adam was standing, and we'd all line up, same height.
Yeah, I got bad joints. It would have been nice if the doctor had practiced first.
Yeah.
Maybe. I don't know. Are we done?
I think we're good. Yeah.
I think we're done. Anyway,
This was a good show, guys.
a lot of interesting topics today, and I'm sure that we will continue to see lots of announcements from different 3D printing companies over the next couple of months. If you didn't know this already, we are on a bunch of different audio podcast platforms now, right?
Yeah.
Okay. What are those? We got Stitcher. We got not iTunes.
Not yet. We need more podcasts.
SoundCloud. All those other ones.
YouTube.
So, and on YouTube.
Google Play
as
Radio is our
always.
latest one.
Really?
Google Play
Okay.
Radio.
yeah.
Okay.
So we're growing. We're everywhere. Make sure you rate us and subscribe, and do all that fun content stuff. Signing off here. Ben, Ken, Kevin, Adam. Thank you for watching.
See you guys.
Have a great day.